Now we can look at the field lines, properties of electric field lines, and what is electric potential energy. Electric field lines is an imaginary line or curve along which a unit positive charge would move in an electric field. That is, the path of a charge in an electric field is the electric field lines. They are representing the strength of the electric field. Actually, they don't exist physically, but we are representing the strength of the electric field and the direction of the electric field, etc., in terms of electric field lines. Then if there is greater concentration of field lines, there is stronger field, and the number of field lines per unit area or density of electric field lines is directly proportional to intensity of electric field. If the intensity is greater, there will be larger number of field lines per unit area. That is N by A, number of field lines per unit area, N by A proportional to intensity of electric field E. In the case of a point charge, consider a sphere with charge at its center and radius r. The number of lines per unit area around the concentric sphere will be N by 4 pi r square. 4 pi r square is the surface area of a sphere. That is, E varies as 1 by r square. Electric field is proportional to N by 4 pi r square. E varies as 1 by r square. This is consistent with the result obtained from Coulomb's law. This from Coulomb's law we have E is equal to 1 by 4 pi epsilon 0 q by r square. Hence we can represent electric field in terms of field lines. These are some of the field lines. Now we can look at the properties of field lines. They start from the positive and end at the negative charge. The number of field lines leaving positive charge and entering the negative charge is proportional to the magnitude of the particular charge. The tangent drawn at any point gives the direction of electric field at that point. If you want to find the direction of electric field, you just draw a tangent at a particular electric line, and tangent will give the direction of the electric field. The field lines do not intersect. This is a question. Show that the field lines do not intersect. Why? Electric field lines do not intersect. Why? If they intersect, at a point of intersection there will be two directions or two alternative paths to travel, which is impossible. Therefore, electric field lines do not intersect. Then, to represent uniform electric field, draw uniform parallel equidistant lines, and it will represent uniform electric field. Field lines are always normal to the surface of a conductor. In the case of a conductor, the field lines will be perpendicular to the surface, and they do not pass through a conductor. That is, hence the interior of a conductor is free from electric field, electrostatic shielding, but they pass through an insulator. These are the properties of electric field lines. Then electric potential energy. Consider two charges Q1 and Q2 at points A and B. Q1 is placed at A and Q2 is placed at B. Consider a small displacement from the charge Q, in which its distance from Q1 changes from R to R plus dr. Initially, if they are at a distance R, it is displaced through a distance R plus dr. The electric force on the charge Q2 is F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square along AB. Then the work done by this force in the small displacement dr is dW is equal to force into displacement Q1 Q2 by 4 pi epsilon 0 into dr. The total work done, if the charge is moving from R1 to R2, total work done we get by integrating dW. W is equal to integral from R1 to R2 dW. It is equal to 1 by 4 pi epsilon 0 Q1 Q2 into 1 by R1 minus 1 by R2. 1 by R square, integral 1 by R square will give minus 1 by R. Giving the limits, upper limit minus lower limit, we will get 1 by R1 minus 1 by R2. Then change in potential energy is the work done by the electric forces. ur2 minus ur1 is equal to q1 q2 by 4 pi epsilon 0 1 by r1 minus 1 by r2. And if r2 is at infinity, that is the second charge is at infinity, ur is equal to q1 q2 by 4 pi epsilon 0 r. This gives the potential energy of a pair of charges. And if there are three charges, q1 q2 q3, then potential energy of the system will be equal to the sum of potential energy of the three pairs. That is, first we have to pair q1 and q2, then q2 and q3, then finally q1 q3 pair, and you have to find the sum of these three pairs will give the potential energy of the system.